Okay, just so you know, the little guy with the clock on it, that lets me know that you've stepped away from your computer. And if y'all need to, that's fine. Just let me know so that I don't try to talk to you or ask you a question. All right, for everyone that is going to be watching this recording after we meet here today for Lecture 1.2, welcome to, thank you, Michael. Welcome to Lecture 1, Section to get used to using the pen here. I don't have my license for this thing yet. No, I'm kidding. It can be tricky sometimes. Okay, so yippee, very exciting. This section starts out with some definitions that we need to know. I won't bog down in these, but we at least need to hit them up so that you can understand the language that's used through the rest of the section. So hang on just a second. Let me see if I can put hands down, lower hands. All right. Okay, so a relation. This whole section is about functions and how they are represented visually on a graph. So this is our supporting language that we'll need to move forward with that. Okay, so in mathematics there is the idea of a relation. A relation, just like you would think of it in regular terms, like if I say I'm related to her or him, then that means we have some sort of connection. Usually when you say I'm related to you, you're talking about a familial connection. In mathematics, a relation is a connection in a sense, but we define it as a mapping of input to output. Any kind of mapping from input to output. So when we're in mathematics, that usually means an X value and a Y value. We input an X value. I'll go ahead and mark that our input is usually our X and our output is usually our Y. And it just sends one piece of information to another place. Now, a function is a relation, but it's a special type of relation. And it is the type of relation that we'll be dealing with for the rest of the semester. So put a star. If you're following along with your notes and filling them out with me, put a star by this word here because it is mucho important. A function is a mapping of, let me say, some input to, here is the important part. I'm going to do it in a different color. One and only one output. In other words, anytime I put an input value in, there's only one possibility of an output value for that thing to be a function. And we'll look at examples of this on the next page to really solidify these definitions with you. Let's just get the language out of the way first. Okay, so domain is the word meaning all possible input values. In other words, it's anything that you can plug in for X in very simple terms. The range is the exact opposite, all possible output values. Oops, that's plural, values. 9 times out of 10 from here on out, you'll be expressing these in interval notation. And I'll go over that later on in the lecture just to refresh you on that. You should be familiar with it, especially if you went through Math 99 here at Georgia Highlands. We teach this, and some of us teach it in Math 97 as well. But I will go through it for you and remind you of all that stuff. I realize how quickly cobwebs form in our brains. Okay. Let's move on. Is everybody good so far? Like I said, I know these are just definitions, and I'll make them a lot clearer with the examples on the next page. Okay, Taylor and Wes are good. Michael, can you give me a green check or a red X to let me know you're cool to move on, or whoa, go back? I don't know if your phone will do it. Okay, I'm not getting anything from Michael. I'm going to go ahead and go forward. Michael, raise your hand if you need me to go back. All right. Oh, do you need me to go back? Go back. No, okay, that's fine. All right, let me clear all those checks off, and I'll put your hand down for you, Michael. All right. Okay, next slide here. All right, so a little more about domain and range and relation and function, visually speaking here. And actually, we'll look at one example of a relation just to see what a function is not. Other than that, your main focus should be functions, functions, functions. Like I said, that's what we're going to be talking about for the rest of the semester. So when I gave you the definition of relation, I just said it maps input to output. So all of these examples here, just these lines moving to another number, a set of ordered pairs, and here graphically represented, these are all relations because I have taken some input value. So in this case right here, I've taken 20 and sent it to 10.7 and formulated the point 20, 10.7. Notice these are representative of all the same set of data. So look, I've sent 0 in this blue to yellow set here. I've sent 0 to 9.1. That's represented by the point 0 right here, represented by the point 0, 9.1. And on our graph over here, notice my scale. I have the point 0, 9.1 living right there. So these are all three of these are representative of the same data set. So these are all representing a function because I have not sent any one input value to 2 or more output values. For a relation to be a function, you can have one and only one output for any input. So notice in this blue to yellow, I sent 0 to 9.1. I sent 10 to 6.7, 20 to 10.7, and so on and so on. If I had drawn an arrow from 10, another arrow, to, let's say I'm putting a new value in here, let's say 11, okay? And I ask you, okay, if I throw 10 into the mix as an input value, what is the output that I get? Well, you wouldn't be able to tell me the single output that I get because 10 is being sent to 2 different places. I would have another point in my set here that would be 10, 11, And watch what would happen graphically speaking, and this is going to come up again in just a minute. So here's 10, 6.7, and if I graphed the point 10, 11, it'd be about right there. I'll do another point. So let's send 10 to another place. Let's send it to 13. So 10, 13 would be about right here. And if either of those points were in here, this function that's being represented these three different ways would cease to be a function at that point. It would then just be considered a relation. So I'm going to blow your minds with a statement and say, all functions are relations, but not all relations are functions, because functions have that very special characteristic of having one and only one output value for each input. So hopefully it's becoming a little more clear. And I will point out, and this may ring a bell with some of you, I will point out that when you have a graph of something that is not a function, because you're sending some input on the x-axis to more than one output, you start getting points stacked on top of each other. So we'll talk about that in a little bit. And I'm sure there are bells and whistles going off in some of your heads about that. We also have another way of representing input and output data, and that's a good old XY table. So if I have an XY table that looks like this, 1, 2, 3, 4, I don't know, I'm just making up numbers, by the way, 9, 10, 11, 12. This is representative of a function. I've sent each input to one and only one output. However, if I have something that looks like this, 1, 2, 2, 3, 4, 11, 12, 13, 14, 15, this is not a function. It's not a function because you can't tell me where 2 goes, that single place that 2 goes to, because it's sent to 2 different places. Let me give you one more example. Say I have 1, 2, 3, 4, 5, 6, 6, 7. Normally, if you were in my face-to-face class, I'd say, oh, is this a function or not? And we'd talk about it, but since I can't really get quick feedback from everybody, I'll just tell you, this is a function. It has sent each input to one and only one output. If I ask you where 1 went, you'd tell me 5. If I ask you where 2 goes, you'd tell me 6. 3 goes, 6. So just because this right here happened in the y values, this thing is still a function. Moral of the story is you can't have multiples in the x column. That's when you start sending a single input to more than one output. And I see Wes is typing. Did you say all relations are functions? Or okay, let me repeat that confusing statement. All functions are relations, but not all relations are functions. Functions are special type of relations in that it sends each input to one and only one output. You good, Wes? Okay, great. Welcome, Trina. Glad to have you. All right. So any questions about these examples that I have up here at the top? Did that kind of clarify in everybody's mind the difference between function and relation and help you see that, you know, you've got multiple representations of functions? Okay, Taylor gave me a green check. Can everybody either give me a green check or a red X on, just to let me know that they understood before we move on? And Trina, I know you just came in here, so I don't expect you to answer on that one. We can just pick up with your understanding on this next concept. So I'm going to clear everybody's checks out and move on. All right. Down at the bottom, we have yet another representation of a function. So now we've got 5 ways to look at functions, and those are functions with equations. Equations and graphs are the main ways you're going to see functions represented in this class, and then as tables as well, because you usually have to have the XY table to move to the graph. So functions are usually given in terms of equations rather than a set of ordered pairs. The variable x represents we call this the independent variable, and is assigned to any value from the domain. So I'll talk about that in just a second. I will finish off filling in these blanks. The variable y represents the dependent output variable and is assigned to any value from the range. For each value of x, there is one, it's important, and only one value of y that corresponds. And this is for this thing to be a function. One and only one corresponding output value. Okay, so the reason we call x, or the input variable, the independent, and y, or the output variable, the dependent variable, is because you usually plug in x first. And you don't know what y is going to be until you run it through its function and get that y value out. So y depends on what you've plugged in for x. So if real quick example, if I have y equals 3x plus 2, and I plug in an x value of 1, in that case, my y will be 5. However, if I plug in an x value of 0, my y value will be 2, and so on and so on. So x is considered independent because you just kind of pull that out of the air. Give or take some restrictions with certain functions. With linear functions, which is what I have there, y equals 3x plus 2, you can choose any real number you want to plug in. So that's why it's independent. You can pull it out of the air if you'd like. The reason that the y is the dependent variable is because it absolutely depends on what you've plugged in for x. So hopefully that makes some sense to you. Here's an example of a function as an equation. This is actually a quadratic function. Just for the record, the reason that 3x plus 2 is linear is because the degree is 1. X is raised to the first power. That's your highest value of your exponent. This particular equation down here is quadratic. I'm having trouble getting my pen to write. There we go. D-R-A-T-I-C. All right. And that is because the degree is 2, or x is squared. So when x is in the first power, it's called linear because it'll graph as a line. When x is squared, or we have a degree of 2, it's quadratic. That graphs as a parabola. And you'll learn probably way more than you ever wanted to about both of those, but mainly about quadratics and even higher order polynomial functions throughout the class. Okay, so before I move to the next slide, give me a green check if you're ready for me to move on, or a red X if you say, whoa there, come on back. Okay, it looks like everybody's good. I'm going to go ahead and move forward. Ugh. I need to plug my laptop up. Oh my goodness, I don't want to die on y'all. Hang on just a second. Okay. All right, so determining whether an equation represents a function or not. These can be kind of tricky, but if you just go back to the definition of a function and see if these equations meet that definition, then you should be okay with it. So to figure out if an equation represents a function, you need to solve each equation for y in terms of x. If two or more values of y can be obtained, then it's not a function, because that's going to send that x value to more than one y value. When I say solve each equation for y in terms of x, that just means solve for y. Get y by itself on one side and see what happens on the opposite side. So I'll do that with both of these here. For this first one, if I want to isolate y, the first thing I'm going to do is subtract 2x from both sides. And I'm left with y equals negative 2x plus 6. So if I plug a value in for x, I'm going to get one and only one value out for y. That's a linear equation. By the way, all linear equations are functions. Oh, I take that back. Unless you have a linear equation that looks like this, like x equals 1, that's a vertical line, not a function, because it's stacked to those points on top of each other. So those aren't functions. So scratch what I said. Almost every linear equation is a function. All right, let's take a look at this next one. So I want to isolate y. I first subtract x squared from both sides. And then I have y squared equals 1 minus x squared. I need to take the square root of both sides to get y by itself. And when I take the square root of both sides, I have to take into account the positive and the negative value of the equation there. That says minus x. Sorry, my pen kind of bled into the other thing. So in this case, let's do a test run here. If I plug in, let me choose a strategic number to, one's not really a good one to do because you get positive or negative 0. 1 minus, okay, so we'll just plug in 30. So if I plug in an x value of 3, and I want to know what y is, I have y equals positive or negative 1 minus 3 squared. So this is positive or negative square root of 8. We would need to simplify that. The same thing as square root of 4. Hi, Kim. Sorry I missed our appointment today. I was transporting my friend from chemo treatment, and I forgot to mark it off my schedule for that. I apologize. No worries on you being late. Sorry for missing our appointment today. I missed my appointment with Taylor, too. So we have positive 2 square root 2 or negative 2 square root 2. So if I throw 3 into the mix, you can't tell me if it's positive 2 square root 2 or negative 2 square root 2. So this thing right here, not a function. As a matter of fact, that's a circle. When you graph that, that's pretty bad. When you graph that, that's a circle. And so you can see you've got points stacked on top of each other with a circle. So this thing is not a function. Everybody get so far? Green check or red X? Dave is typing something. Okay, so Taylor says green check. Wes says no. Is square roots normally not a function? That is a good question. It depends on, okay, it depends on if there's a y squared in it as well. So if I have y equals the square root of x plus 2, that is a function. But it's because I have to take into consideration the positive and the negative when I'm using the square root property like that. Maybe this will help you. I'll explain to you why you have to consider the positive and the negative there when you're solving that equation like that. Let's take this equation, for example. X squared equals 9. Nice, neat, small numbers to think about. This statement here says, what number can I multiply by itself and get positive 9? Well, I could plug in 3. Okay, so everybody started putting 3 in. However, I could also plug in -3 because Kim said -3 times -3 is positive 9. So when you are solving equations of this manner, you would take the square root of both sides to get x by itself. But because of the nature of the original question, this answer right here could be positive or -3. This is not set up like a function, though. We have to have an x and a y to have a function happening. That I just did off to the side will explain why I had to write positive and negative x, because I had a statement that said something squared equals 1 minus x squared. So this first part right here says, what can I multiply by itself to make this thing over here? You can multiply the positive or the negative by itself to make that. So when you're solving square root equations that have 2 variables in them, yes, you're going to end up with not a function. However, it's going to, if you're solving for y, the y's got to be squared for you to have to take the square root of it. If you have y equals x squared plus 2, that's just a quadratic. That is a function and it has no restrictions. To be a function, you can only have one domain and range or one answer. You can, okay, when you use the words domain and range, that's talking about the entire set of values. So there's only one domain and range for any function. You can only have one output value for every input value that you put in. Hopefully that cleared things up, Trina. I'm not sure if it did though or not. This can be a tricky thing to wrap your brain around when you're looking at the equations. So here's my nickel's worth of free advice. If you see a y squared in there, it's not going to be a function. Because if you have y squared and you're solving for y, you're going to have to do this step here, which means you're going to have to take into consideration the positive and the negative. I'm getting a text message. Did that clear things up okay? I don't want you to get too bogged down into this. Our main concern really is that we can identify them graphically and know that you can't have doubling up within your domain. And Trina, I hope you didn't feel like I was patronizing you with your language there, but I just want to be extremely clear with everything. Okay, very good. Okay, so give me a green check. Well, actually, let me clear them off. All right, give me a green check if you're good, or a red X if you still want to talk about this before we move on. Okay, I'm getting some green check. Everybody's green check. Let's move on. Okay, so hang on just a second. Let me make sure that wasn't an important text. Okay, so function notation. Okay. So my family's flying in today from Colorado, so they were letting me know that they were good and getting ready to get on their plane. Function notation. The whole idea of function notation is that f of x is equal to y. Okay, so let me clear up a couple things about this part of the notation. This is absolutely not multiplication. That does not say f times x. What this means, this is a symbol itself altogether. What this symbol means is the function of x, how x acts, the function of x. The language that we use, and you probably just heard me say it, we say f of x. The function of x is the same exact thing as y, because y is the function of x. If you chunk x into the mix, it goes through what it's going to do. How it performs or how it functions is what you get out as your y value. So a minute ago I wrote an equation, y equals 3x minus 2. I could have written that same equation, f of x equals 3x minus 2. Same exact thing. F of x is y. So another familiar one to you, y equals mx plus b. F of x equals mx plus b. There's your slope-intercept form right there. So don't let it freak you out because it's just notation. Now the reason we use this notation is so that we can name different functions with different letters. So you might say g of x. If you have two functions, you have an f of x and a g of x. You can have an h of x. You can have a t of x, you can have two different variables. Say you're doing an application problem and you input time and you get out speed, or actually position, but we won't go there. So say these are the points in all the plane for your application problem. Your function would be s of t equals, I don't know, 0.5 t plus 7. I'm making this up. So this is just notation for functions. And whatever is listed inside the parentheses in the notation, so in this case I put a t in there, that is the variable that's going to be the input variable on the opposite side. But you can also place values or other functions in there. So if I have something like whoa, that was bad. Actually, we'll just go to this example down here to talk about that. So here's my function. F of x is x squared plus 3x plus 5. That is a quadratic function. If I want to know what I get when I plug in 2 for x, I can simply write, well, Tell me what f of 2 is. And all I've done is replaced the x variable in there with a 2, and that is just telling me to go and plug in 2 wherever I see x in the function. So this is what that looks like. F of 2 is equal to 2 squared plus 3 times 2 plus 5, 4 plus 6 plus 5, which is 15. So I have a few ways I can write this. F of 2 is 15. There's function notation. Sorry, my throat's getting really dry. F of 2 is 15. This corresponds to the point 2, 15 on the function. Remember, f of x is y, so f of 2 is 15 is the point 2, 15. I plugged in 2 for x and got out 15 for y. This is a point on the graph of this function here. This function is going to look something like this, sitting in the plane. And sure enough, you would find the point 2, 15 on the function. So these are the two main ways that we would represent that data, or we could represent it in an XY table. All right, moving to the next one. Actually, first, are there any questions about, we call this evaluating a function, when you plug something in and see what you get back out of it. Are there any questions about A there? Okay, Dave is typing something, so I'm going to hold on first. And Michael's typing. Okay, Michael says no questions. No, I'm lagging. Okay. All right, so I'm going to move on to the next one here. This says f of x plus 3. In other words, if I replace x in my function with x plus 3, what do I get out? So f of x plus 3 looks like this. X plus 3 squared plus 3 times x plus 3 plus 5. Okay, let me just dispel a rumor. X plus 3 squared is not x squared plus 9. X plus 3 squared is x plus 3 times x plus 3. You've got a middle term there. You've got to be very careful of that. I need to distribute this 3 here, so I get plus 3x plus 9 plus 5. X plus 3 times x plus 3 is x squared plus 6x plus 9 plus 3x plus 9 plus 5. And now I combine like terms and get x squared plus 9x. See, 18 and 5 is 23, plus 23. So the function of x plus 3 is x squared plus 9x plus 23. And now this is going to look really confusing, but don't worry if it's really, I'm just writing it for posterity's sake. This corresponds to the point x plus 3, x squared plus 9x plus 23, if I write it in point form. So we have our function notation and our point notation. Once again, going back, the whole idea is f of x is y. And if I replace the x inside the parentheses with something different, that just means take that something different and go plug it in wherever you see x in the function. So this last one, f of negative x, that is equal to negative x squared plus 3 times negative x plus 5. Negative x squared is x squared. 3 times negative x is negative 3x, and then plus 5. So my function notation, f of negative x, is x squared minus 3x plus 5. point notation, I have negative x squared minus 3x plus 5. Is everybody cool with understanding how to read function notation and evaluate a function using function notation? Green check or a red X? Green check, green check, green check. I'm waiting on Trina and Michael. Okay, Trina came in. Michael, are you all right? Okay, very good. We'll move on. Okay, sorry this is a little fuzzy. I had to take screenshots of my notes and put them onto the PowerPoint slide. All right, graphs of functions. The graph of a function is simply the graph of its ordered pairs. Your calculators. We can use a graphing utility, that's what they call your calculator in your textbook, and tables and graphs. In example 5 for the functions, f of x is 2x, so we have a linear function there, 2x. And g of x, okay, so there's that naming system. We have another function, so we just call it a different letter of x. G of x equals 2x plus 4, also a linear function. Now, if you put both of these functions into your calculator at the same time, and in the first lecture I showed you how to do that, you go to the y equals button at the top left of your calculator, and you'll see a screen that says y1 equals y2 equals y3 equals. You just put two different functions in there, and it'll graph them on the same graph, just like we have pictured here, and it'll put them in the same table. So usually my students are okay with looking at a graph with two lines or two curves on it, but looking at a table that's been set up for two different functions can be a little bit confusing. So let me explain what you're looking at here. When in your calculator, when it sets up a multiple function table, it uses the same x input value to give you the output value for both of your functions. So what this first line here says is when I threw -2 in as my input value, for the function, my first function, 2x, I get out -4. For my next function, 2x plus 4, I get out 0. That's how you read these tables. Now, you're going to be asked questions in your homework and on your quiz about specifically about these tables. So one question that you might be asked is, oh, actually these don't cross. Never mind. I can't show you that here. Let me give you a hypothetical situation. So let's forget that this is a table for these two lines over here. They're parallel. They're never going to cross. But let's say we had this table here set up for two functions, and I'm going to change a value in there to make my example worthy of talking about. Let's say that when I put in -1, so I'm looking at the second row here, let's say when I put in -1 into the function that I got -2 and -2 out, that I got the same y values out for each of the different functions. That would indicate that this is where the functions cross. They have that same point in common. So if I've got two lines and they have one point in common, so I'm talking about where they're crossing each other, then that's going to be the same point. They're going to have the same x value and the same y value. So those you may be asked some questions in your homework about stuff like that. Where do these two functions cross each other? You may be asked, what are the y-intercepts for each of these functions? Well, we talked about x and y-intercepts in our last lesson for section 1.1, and you figured out that every y-intercept has 0 as its x value. So if you look right here in line 3 of this table, when I plug 0 in for x, I'm getting my y-intercept. So for f of x equals 2x, my first function, the y-intercept is the origin, 0, 0. For my next function, 2x plus 4, the y-intercept is 0, 4. So it's up on the y-axis from the origin. Is everybody okay with this? Okay. Check, 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 check. Check. Michael's typing something. Okay, great. Thanks, Michael. Okay, so looks like everybody's good to go. Go ahead and clear that out. Not every graph in the rectangular coordinate system is a graph of a function. The definition of a function specifies that no value can be paired with 2 or more x values. I'm sorry, values of y. Pardon me. Consequently, if a graph contains 2 or more points with the same x values, that graph cannot represent a function. So it's restating what we've already been talking about, just trying to solidify and make sure you get it. So, and this is what I think that a lot of y'all had in your mind back on that first page when I started stacking the points on top of each other and said this is not a function. Notice the coordinates for the points here, 0, 0, 0, 1, 0, negative 1. They all have the same x value. So I've had multiples of the same x value going, in this case, to 3 different places. And what happens is it starts stacking those points on top of each other when you do that. So what this allows us to do, that characteristic of sending an input to more than one output, allows us to do a very quick visual check of a graph to see if it's a function or not. That's what the vertical line test is. The vertical line test says if any vertical line intersects a graph in more than one point, some input for the graph has been sent to more than one output. Therefore, the graph does not represent a function. So the vertical line test is basically a visual test for a graph to see if it represents a function. So if I am looking, if I'm looking at this graph over here, this S-curve graph, here's how we do the vertical line test. We come in and we start drawing vertical lines. Okay, cross through one point, I'm good, 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 good. As soon as I hit it stacking on top of each other, it fails the vertical line test, and that says not a function. So when I said to you earlier, oh, that thing that's x squared plus y squared equals 1 when we were trying to figure out if that equation represented a function, and I told you that that actually graphs as a circle, it fails the vertical line test. It passes through more than one point. Everybody good on the vertical line test? Check, check. Check, 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 check. Okay. Yeah, that's a pretty simple concept. It And check from Kim. Sorry I didn't wait on your check, Kim. Okay, so obtaining information from a graph. You can obtain information about a function from its graph. At the right or left end of the graph, you will find either closed dots, open dots, or arrows. And actually, you can find open dots inside the function. It doesn't have to be on the ends of a function. So let me just tell you what these mean. Closed dots mean the point exists, but the function terminates, ends. So an example, maybe closed dot, arrow. On this end, that point exists on the function. It's an actual x, it's got an x and a y value, but it doesn't go past that to the left. It doesn't go more negative than that. The closed dot means it ends right here. The arrow, on the other hand, means it continues on in this manner. So I'll go ahead and define that continues in the same manner. So for that particular one, it's going to keep on going to positive infinity in the y direction. An open dot means the function's point does not exist there. And I would say it terminates. It terminates if you have that on the end of the function, like, let's see, put a parabola type thing. We'll put an open dot there, and I'll put an arrow here. This means this function exists all the way up until the open dot. I tried to put an x value in, but got no y value out, and it ends right there. However, you can have an open dot in the middle of a function, and it means that the function does a jump over that point. So say we have something like this, some sort of cubic. So it doesn't mean it terminates. It just means there's no value for the function there. So with this particular one, it just skips over the whole. If you go on to calculus, you'll learn a lot more about the holes and all that sitting in there. We'll learn a tiny bit about it in 2.6. Is everybody good with closed dot, open dot, and arrows on a graph? Yes, 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 yes. All right. I'll take that as an overall yes. Interval notation. Let me clean up my screen here so I have enough room for all of this business. We have 2 slides left after this. I will be very soon after 4 o'clock. I won't have you much past 4 o'clock, but we will probably go over a little bit. Sorry. Okay, interval notation. If you need to leave, feel free. Interval notation. If you think about the word interval, it means, you know, from here to here. It's a chunk of something in plain speak. So interval notation allows us to write an unbroken set of numbers instead of having to list out. Say you had all the numbers from 1 to 10. And everything in between there. And you didn't want to write 1, 1.1, 1.11. I mean, they're infinite numbers just between 1 and 2. So the way we write that is using interval notation. So if I wanted to write everything including and between 1 and 10, I'd write it this way, and then I'll go back and explain So I'm talking about the interval from 1 to 10, and we say inclusive, meaning it includes 1 and it includes 10. So here's some notation. Just like when you used to graph on the number line, like, let's see, there's 0, 1, 2, 3, 4. Say I wanted to talk about all of the numbers greater than or equal to 1. I draw a closed dot and then color the arrow. There's flashbacks here for you. Color the arrow that way. Interval notation corresponds to number line notation there. So if you're familiar with graphing on a number line, you have open circles and closed circles on the number line. An open circle means do not include this number, up to but not including. The closed circle means up to and including that number. So I would include 1 in my little graph up here. If I didn't want to include 1, I'd draw an open circle on it. So an open circle in interval notation corresponds to a parenthesis. And using a parenthesis means up to, but not including. So if I write the interval, and let me finish talking about it, and then I'll give some examples. We have a closed dot in number line notation, which corresponds to a bracket in interval notation. And that means up to and including. So if I have the notation parenthesis 2, 5, bracket, on the number line, that would look like this. There's 2, 3, 4, 5, 6. This means I'm talking about all of the numbers. Let me get a different color here. All of the numbers between 2 and 5, not including 2 though. Now, 2.000001 is included, but the actual number 2 is not. So I could have also graphed this using an open circle here and a closed circle here. It would mean the same thing. Interval notation is universal. Like you can send something in interval notation to Europe and they'll know what you're talking about. So it's a way to talk about unbroken intervals of numbers. And like I said, there are infinitely many numbers between 2 and 5. We can't list them all because you can always add another decimal place on something and that's a new number. So a couple of other things about interval notation. Say you have an interval, skip over a chunk and have another interval that all satisfies the same thing. You use the union symbol between your intervals. That's a U without a tail. This is union. And it means either or. So you can either be in this interval, union, or that interval over there. I'll give you an example. -1 to 2 or 2 to 6. So what this says is include -1 in the interval all the way up to but not including 2. Then you skip over, or you can be from 2 but not include it up to 6. So 4.97371 would be in the second interval there. One more thing to talk about with interval notation is infinity. For our number line, we have, here's 0, we have negative infinity and positive infinity. Just keeping on running out in the same direction. With negative or positive infinity, you will only use parentheses. Because you can't include infinity. You can't say, I'm going to go grab that piece of infinity, because you'd be grabbing a number, a value. The very nature of infinity says, I can't go grab a piece of it. I can't include it. So you always use a parenthesis when you're talking about infinity. So I told you with linear functions, y equals 3x minus 2, the domain is any real number you want. You can choose any real number you want, multiply it by 3 and subtract 2, and you'll end up with a real number. So the domain here, the domain for this function is negative infinity to positive infinity. Let me give you one more example. Y equals the square root of x. This presents a different issue. I don't want to take the square root of a negative number. That creates imaginary numbers. So the only possibilities of plugging in for x into that function are 0 up to positive infinity. I can't plug in negative numbers. The square root of negative 1 is I. That's an imaginary number. So the domain for this function, and I should have written it in function notation, f of x, g of x, the domain for this function would be 0 inclusive, because I can plug in 0 there. The square root of 0 is 0, and that is a real number. 0 up to positive infinity, non-inclusive, because I never include infinity. Is everybody good with interval notation? Yay! I'm glad to be seeing green checks coming through. Yes! All right. Okay, domain and range. So this can be a little tricky. So pay close attention here. I'm going to make up some arbitrary numbers so that we can understand this graph. We'll say that this first x value is 3, and the second one is 11, and then we'll say that this is 4, and I don't know, 14. Okay. So when you are talking about domain, you're talking about all possible x values, all possible input values. So I want to write the domain of this function in interval notation. You can see that we're basically talking about the span, the horizontal span of this function. So if I drop dotted lines down to give me some boundaries, in the left and right direction, when we're talking about domain, in the left and right direction, this function exists between 3 and 11 inclusive, because there is a closed dot on both ends. That means that those points exist on the function. They have y values. So the domain for this function would be 3 to 11 inclusive on both ends. Therefore, 3.00007 is included in there. You could plug it in and get a y value out that lived on the function, that lives on the function. This is where it gets tricky for students when they have to flip their thinking here, the range. So since domain is talking about the left and right span of the function, the range is talking about the up and down, or the vertical span of the function. So my function lives between. Now notice I didn't go to the top point here, or the end point, because my function lived above that. So I had to mark the boundaries that contain the entire function in its up and down manner. So the range for the function, and by the range is your y values or your y span, the range for this function, because it actually has a point up there at the top, and the point exists at the bottom of the span as well, then this range is from 4 to 14 inclusive. Anybody have any questions so far? Because we're going to look at these examples at the bottom. Okay. I don't think anybody has any questions. Thank you, Dave, for the, oh, I saw a green check. Probably meant you were okay. Raise your hand if you have a question, and I'll stop and go back. Because this, like I said, this can be tricky. All right. So I want to state the domain and range for each of these functions. So for domain, I want to talk about the left and rightness of it. So I'm going to drop my boundaries down to contain my function from left to right. I've got closed dots on both ends. The domain for this function is -2 to 1 inclusive. I'm going to do just the opposite for the range and contain the up and downness of the function. And here's where I'm probably going to get questions. The range for this function is from 0 to 3 inclusive. Oh, one major important thing I forgot to say about interval notation. Highlight this. You state interval notation in number line order. In other words, it would be wrong for me to state that range from 3 to 0. So you want to go from least to greatest when you're stating your interval notation. It's always least to greatest, just like it is on your number line from left to right. Hopefully that was clear. Does anybody have any questions about that first one? Raise your hand if you have a question. I'll give you a minute to digest. I'm going to pour myself another glass of water. I'll be right back. Okay, so it looks like everybody's cool with that first example. All right, see if you can do that second example on your own. Take a moment. I'll turn on some music so it's not awkward, or maybe it will be more awkward when I turn my music on. But go ahead and take a moment and see if you can state the domain and the range of that second function, just to make sure that you know what you're doing. If you want to type what you got in the chat window, I would love to have you do that. And you can just type D:R:. Taylor and Kim are typing. Wes is typing. Okay. Let me check it, Taylor. You got it, Taylor. Negative 2 to 1, negative 2. Question mark? Okay, it looks like everybody got it that typed it into the window down there. That is awesome. Okay, so for those of you that didn't put your answers in there, I got to say, very good, Ken, thanks. For those of you that weren't so sure, I'll give it a go here for you. Let me tell the music again. All right. So here's my left and rightness of my function, which is my domain. My domain goes from negative 2 non-inclusive to positive 1 inclusive. And my range, the up and downness of my function, goes from negative 1 inclusive to positive 2 non-inclusive. So hopefully everybody's cool with that. Raise your hand if you have a question though. Now this last one's a doozy. So first of all, I'm going to show you that the left and rightness of this function is unbroken. In other words, there's a value at every point where it is. So I have a value for the function at negative 3, negative 3 point, or negative 2 point something. At negative 2, I don't have a value for the function there, but I've got a value for the function there. So there is a value for negative 2 in the function. Same thing, this is called a step function. Same thing with the next step. The only thing that's drawn on here where there's no value for the function is the y-intercept right there. Okay. So that being said, this is a tricky one. Makes you think though. That's good. All right. So let me go back to blue to be consistent with domain and range. All right, so the left and rightness of my function is unbroken from negative 3 inclusive to 0 non-inclusive. That's not the hard one to grasp. It's the next one, the range. So, if I contain my function in its up and downness, I've got no values here for the function. I've got no values here. As a matter of fact, I've only got 3 y values for that function. I've got negative 3, negative 2, and negative 1. This is not an interval. Those are it can't be negative 2.457. It's just negative 3, negative 2, and negative 1. You cannot write this as an interval. This range is the set negative 3, negative 2, negative 1. Green check or a red X? Wow, if I get green checks from everybody, that'll be the first time I didn't have a million questions about C. I've been using that same example for over a year now, and I always have questions on it. Okay, Kim D, all right with that? Wes, are you okay? All right, yes. I need to go buy a lottery ticket today. Last slide. Thank y'all for hanging in there with me. Identifying intercepts from a function's graph. This is not rocket science. It's just where intercepts or where the function crosses an axis, either x or y. We have x-intercepts and y-intercepts. So you can see they've already got them marked here for you. This particular function has 3 x-intercepts, -2, 3, and 5, and it has 1 y-intercept. You can have multiple x-intercepts with a function. You will always only have 1 y-intercept with a function. If you have 2 y-intercepts, it's stacked points on top of each other, and it's not a function anymore. You can have multiple x-intercepts and still pass the vertical line test, as this does here. But if you can't have 2 y-intercepts or you stacked points. Hopefully that's clear to everybody. Okay. By definition of a function, for each value of x, we can have at most 1 value for y. What does this mean in terms of intercepts? That's what I just told you. You can have multiple x-intercepts, but only 1 y-intercept for it to be a function. Okay, so just to clarify, this end on this function is an open circle, and the end on this side is a closed circle, just in case you couldn't see that very well. And let me take these intercepts off so we don't get confused when we're writing domain and range. All right, so what is the function's domain? Let me go back to my blue pen for consistency's sake. So the up and downness, the left and rightness of this function. So I want to drop my boundaries for left and rightness of the function. The domain for the function is, looks like, -3 non-inclusive to +6 inclusive. Actually, we've already answered 3 and 4, so you can cross those off. What is that? Yes, Kim. Kim's typing, so I'm giving her a moment. Would the intercepts be expressed as point? It depends on how they ask it. You can either express it as a full point. So, for example, one of the x-intercepts might be -2, 0. Sometimes we just write x equals -2, 3, and 5. If it's understood what we're talking about. But they are ordered pairs. They do have an x and a y value. Good. Glad that helped. And you can click on your hand again and it'll put your hand down. Okay. All right, so hopefully everybody's cool with the domain. And I saw Trina typed in a smiley face after I wrote the domain, so hopefully that means she got it right on her own. Now we'll look at the range. So try to do that while I'm marking it on my paper. So it's the up and downness. And for the range, I'm getting that it goes from -4, ooh, that's an open circle. Let me change that. -4 non-inclusive, because of the open circle at the bottom, up to +4 inclusive, because I have an actual point at the tippy top there. Okay, hopefully everybody understands that. Raise your hand if you don't. I'm going to go ahead and move on to question number 5. And I'm going to erase everything I've drawn on the graph because this is another one of those topics that can be tricky for students, and I want you to be able to see the graph. All right. So, f of 1. Go back to your understanding of function notation. Your definition of function notation says f of x is y. So when you are asked, what is f of 1? Well, you don't have an equation to plug the number 1 into, but you've got a picture. of what the equation represents. So this is telling you, when I plug in 1 into this function, what do I get out on the graph? If I put an x value, I've got that circled there, if I put an x value of 1 into the function, I get out, well, let's see, I'm going to just draw a line up to see where it meets. And it looks like, remember I told you those can represent points as well. It looks like the point 1, 4 exists on the graph. So f of 1 is 4 in function notation. We'll have plenty of those to practice with in your homework. Trina, I see you're typing something. Once again, while she's typing, all f of 1 says is if I replace x with 1, in other words, if I plug 1 in, what do I get out? Well, if I plugged 1 in and I had the 0.14 on the graph, then I had to have gotten 4 out. Okay, so thanks to, I love this online. Yay! Got to go. Have a good night. You too. Thanks, Trina, for coming. Okay, that was it. Is there anybody that has any questions left? Raise your hand if you're just still like, I don't understand something. I'm going to go ahead and switch to the last slide while I'm waiting on everybody to respond. Okay, sounds good, Dave. All right, well, if nobody has any questions, I will see everyone hopefully tomorrow, if you want to come to tomorrow's lecture over on 1.3 at 3 o'clock. If not, I'll see you in virtual land. Taylor, I'm staying in the room to do your homework help video. Wes? Press your talk button, Wes, or it won't, we can't hear you.
Okay. Can you hear me?
Yep.
Okay, back on function notation, when you said evaluate the function f of x equals x squared plus 3x plus 5.
Hang on.
Few slides back.
Let me turn my microphone up. I was having trouble hearing what you were saying. I can hear you, but I'm having trouble hearing you. Say what you said again.
Back on where you did function notation, and then f of x equals x squared plus 3x plus 5. Let's say you plugged in 3a for the x. Then what would you do?
F of 3a?
Yeah, I saw that in my math lab earlier.
Yep. You're going to put 3a in wherever you see x. So 3a squared plus 3 times 3a plus 5. So this is 9a squared plus 9a plus 5.
Okay. I didn't get that earlier.
Okay, you good?
Yep, I'm good now.
Great, thanks for using your video. It's exciting.
I like it.
Cool, cool. Have a wonderful evening, Wes. I'll see you soon.
Thank you.
Bye-bye. Okay. Taylor, let me stop the recording. Okay. I guess Hannah's going to stay. Hannah's going to stay for the homework help. Is that okay with you, Taylor?
Yeah, that's fine.
Okay, great. All right. So go ahead and tell me what your first homework problem is that you were having issues with.
Okay, we just went over it, but it was does y equal the square root of x plus 37, define y as a function of
Okay.
x. I mean, I know how to plug it in, but I was just confused.
Y equals the, say it again, hon.
The square root, and inside the square root is x plus 37.
What x plus 37?
Just
Okay.
x.
Okay, so it's telling you to define y as a function of x. So it's asking you, is this a function? Okay, so let's give it a test run and see if we get more than one y value out. If we get more than one y value out, this thing is not going to be a function. So I'm going to make this super simple on myself. And actually, let's not change the function notation because we're not sure if this is a function yet or not. Let's plug in the value 12 for x. So that would be y equals the square root of 12 plus 37. I'm very strategic about this. Y equals the square root of 49. Y is 7. So you tell me.
Okay.
It is a function. I put in a value of 12. The only thing I'm going to get back out of that is 7. Now, if this had said y squared equals x plus 37, and you still needed to isolate y, so you take the square root of both sides, there's that situation that's going to be set up to make you have to go positive or negative square root of x plus 37. This would not be a function. Not a function. This, however, because you're going to get one y value out for any x you put in, this is a function.
Okay.
Since that was a pretty quick one, do you want to look at another one? Because you're going to get one value out for any x you put in.
Okay. So you can plug anything into x, right?
Well, since this is a square root, you got to be careful because you don't want to plug in. We call this their restriction.
Section 1.2, and it says find g, and then in parentheses it says 8, and let g of x equal -4. Okay. It says find the ordered pairs for equation y equals x to the cubed minus 2.
Okay. A cubic.
And could you just make the x value equal anything? Because I chose -3, -2, -1, and 0. Okay.
That is fine because there are no restrictions on the domain. You can cube any real number that you want to. Cubing is just multiplying something by itself 3 times. So there are no restrictions on cubing a real number. Now, if that thing were a square root or something like that, you'd have to start thinking, oh, is there a possibility of getting an imaginary number? But for this, you can cube anything you want to. And I'll go ahead and finish off this XY table for everybody else to benefit from this problem. So the first thing I do is plug in -3. -3 cubed is -27. -27 minus 2 is -29. So that corresponds to the point -3, -29. -2 cubed is -8. -8 minus 2 is -10. -1 cubed is -1. -1 minus 2 is -3. 0 cubed is 0. 0 minus 2 is -2.
Okay.
You want to do your last one?
I didn't have another one.
Great. Well, thank you so much for being the guinea pig with the homework help video. I appreciate it, and I'm going to go ahead as soon as it sends the recording link through to me. I'll go ahead and post it for everybody else to give a look-see. Have a good evening, Taylor. Bye, Hannah.
Ah.